I'm going to explain limits. Now, a limit is the number L that y approaches for a function as x approaches c. So this allows us to figure out, alright, what number does y approach, or what number is y, essentially, as x approaches c, or x becomes c. And you'll notice I have this little f of x here. Now, keep in mind, that is essentially the same as y. So it indicates y equals then some function. So this is just how I model the function with the f of x. So this allows us to figure out the limit as y approaches L as x approaches c. Now, for an example, I'm going to have the function f of x equals x, like that, or y equals x. They're the same thing. F of x and y are the same thing. Now, for this, we would plug in. Now, there are a couple ways we could do this. The first one is we could have x approach c, which in our case, c will be 1. And we could have it approach that by just plugging in numbers for x. So we could have x be like 0.9, which means y is 0.9. Or we could have it be 0.99, which means y is 0.99. Or we could have x be 0.999, which means y is 0.999, and so on, just kind of going on forever, indicating that as x approaches 1, y approaches 1 as well. Now, you have to do it from the left, which is, this is from the left, this is essentially going this way. We also have to do it from the right. That is an important thing for limits. So we also have to plug in like 1.1 for x, 1.01, and then 1.001. Now, it's okay here because we see that in both situations, y still approaches 1. So this limit is good. Now, the other thing we could do is, instead of plugging in numbers, we could also look at the graph of the equation, which I have drawn here. So we have y equals x, and we see that as x approaches 1, we look up at the graph, y also approaches 1. So the limit as x approaches 1 of the function x is 1. So that's just generally how you do a limit. Now, in most cases, the limit as x approaches c of a function, f of x, that limit actually equals f of c, or if we were to just plug in c for that x. In a lot of cases, these two equal each other. However, there are a couple where that just doesn't quite work, and I'm going to show you them to you. Now, the first one is if we have the limit as x approaches c of a function, but if we just have that function, that we have c be at the bottom, of whatever is on the top, when we have c at the bottom, we get 0 on the bottom. And of course, anything divided by 0 is no. We can't divide anything by 0. Now, we don't necessarily... Now, an example of, say we have like 1 over x, and we have the limit as x approaches 0, well, that would give us 0 on the bottom. Or we could have 1 over 2 minus x, and we have x approach 2. Well, that would also give us 0 on the bottom. So I'm just showing you that if we ever have the limit approach a number as and if we just plug in that number for the equation, we get 0 on the bottom, that doesn't work. Now, there is a way around it, but it only works if you can cancel the x out of the equation. Like say we have x squared plus x over x. What we can do for that is we can factor out an x, and so we have an x, so we can just cancel those x's, and that leaves us with x plus 1. So that way, if we plug in 0 to our x plus 1 equation, we get 1. So in this case, the limit as x approaches 0, is 1 for this equation right here. Now, whenever you're doing a limit like this, if you just plug in the number in its natural form, you get a 0 on the bottom, you can just always do this method. Because if there's ever a situation where you can't cancel the x out of the bottom, such as this situation, the limit doesn't work. And I'll explain why it doesn't work later. Now, aside from if we have a cancelable 0 at the bottom, which means that we can cancel the 0 out of the bottom of an equation. The other use for limits is if we have x approach infinity, because infinity isn't a real number, so we can't just have it plug it into the equation. And there are essentially three scenarios for this. The first one is if we have the limit as x approaches infinity of 1 over x. And this is 0. And I'll explain why that works. Now, for a limit, we can creep up on it. So, say we plug in 10 for x, so we have 1 over 10. That gives us 0.1. Well, now say we have plug in 100 for x. And that gives us 0.01. So, as the x value gets bigger and bigger, the y value approaches 0. You know, it's kind of just the idea of a limit. Now, the second situation for this is, say we have the limit as x approaches infinity, and we have just x. Well, as x approaches infinity, and we just plug it in for x, that means that y equals infinity. It's, it's kind of the idea of y equals x. It's, it's kind of like, well, if y equals this, well, if y equals x and x is infinity, that means y is infinity. Now, our third and final situation is if we have the limit as x approaches infinity of x over x. And in this situation, the x's just cancel and we get 1. Because that's how it works. We can, before we even find the limit of it, we can just cancel out the x's and we'll get 1. Now, say we have coefficients in front of the x's. Say we have, 2x over 3x. Well, the x's still cancel, but now we're left with 2/3. So, if you have coefficients, you look to those. Otherwise, you just, cancel the x's. Now, there's another twist to having x approach infinity, and that is, say we have a polynomial. Like, say we have x squared plus x plus 1 over x squared minus 1. So say we have that polynomial, and we want x to approach infinity. Well, what we can do is we can ignore all these other terms except for the x squareds. We just look at the highest powers. And to explain why we only look at the highest powers is, say we plug in 10 for x. Well, 10 squared is 100. 10 squared is 100, which is bigger than just 10. Or if we plug in 100. Well, 100 squared is 10,000, which is bigger than 100. As such, infinity squared is bigger than just infinity. Now, they're not real numbers, so it's kind of a weird concept to think about, but it's essentially think about, the highest number that exists, which, there isn't really a highest number, but let's say that there is a highest number, and we square that. Well, that highest number squared is going to be bigger than just the highest number. That's kind of the concept. So, since it's bigger, it overpowers these other numbers. So we can just ignore this whole section of the equation, essentially just erase it. So we just look at the higher powers. And then we go back to our original kind of three situations. For example, this situation, we have x over x. We have x squared over x squared. So that means that those two just cancel, so we're left with the third situation, which I wrote in red. So this would be 1. So this is situation number 3. We look to that. Now, say we have, x plus 1 over x squared minus 2x. In this case, we look at our first situation, which is written in blue. So this will be as x approaches 0. Because, we can ignore this section, so we just look at the highest power, and since the highest power is on the bottom, and not at the bottom and the top, it's essentially as though this were just 1 over x. So that's essentially the same situation. Now then the third situation we can come across is if we have the highest power at top. Say we have x squared plus 3x over 1 minus x. Well, in that case, we can ignore all the lower powers, and we just essentially have x at the top, so that would then be infinity. Now, another situation is negative infinity comes into play for if we have our second situation of x on the top. Now, negative infinity is like infinity, where infinity is the largest number. Negative infinity is essentially the smallest number in a sense, or really the most negative number. It's essentially the negative version of the largest number. So, for this, if we say we plug in negative infinity into here, well, since it's x squared, any negative squared, which is a negative times a negative, that gives us a positive. So we kind of have to look at, say we plug in a negative infinity to this. Now, if we plug in a negative infinity to the third or first situation, it's still fine. We still get 1 or 0. But if we plug it into our second situation, we have to look at the power. If the power is even, it gives us an even, our infinity then becomes positive. While if the power is odd, say we have 3, it then becomes negative. We're plugging in a negative infinity. We also have to look at coefficients for here. Like, say we have that times negative 3, well, then it becomes negative because we're multiplying it by a negative number. So it's all kind of looking at signs. So if negative infinity is thrown into the mix, or if you're given a negative coefficient, you kind of have to look at, alright, so it may not be infinity, it may be negative infinity. Now, the last thing we have is there are actually 3 situations where limits just do not work, they do not exist. Now, for our first situation, we're going to have, a nice little graph here. And we're going to say that the graph oscillates, which means it goes up and down really fast, like that. So it essentially goes up and down, we'll say between like -1 and 1. So it rapidly switches between 1, -1, 1, -1, 1, -1, 1, -1. It's actually so rapidly that it's almost at all of these points between 1, -1 at the same time. I mean, it's not really possible, but it switches so rapidly that we can't figure out what the number approaches, so the limit just does not work here. So that's our first situation where limits do not work. Our second situation is if the limits from the left and the limits from the right do not approach each other. Like, say we have the limit from the left is -1, while the limit from the right is 1. Well, since they don't equal each other, I mean, we can't really have a number. I mean, this isn't one limit, essentially, right? Well, if we look at from the left, it's -1. Well, if you look at from the right, it's 1. And since we don't have a preference of whether looking at the left or right side for a limit, this limit does not exist, because the limit has to equal itself from both sides. Now, the third situation where a limit does not exist is if the limit essentially goes asymptotic like this. So, if our equation is like this, the limit essentially just kind of goes up on forever. Now, in a sense, the limit approaches infinity, but since infinity isn't a real number, I mean, it's more of a concept instead of an actual number, this doesn't work. Now, going back to our 1 over x, which I explained that does not work, well, that actually breaks 2 of the laws. First off, we see that it's going asymptotic to 0. It's, from the right, it's approaching infinity, while from the left, it's approaching negative infinity. And that also breaks our second rule, the one in green here, which indicates that a limit has to equal itself from both sides. And you see here that the limit does not equal itself from both sides. So that's why the x has to cancel, because if it doesn't, you're going to get something like this, or maybe something like this. But nevertheless, these are the 3 situations where limits do not exist. But yeah, that was how you figure out the limit of an equation. I hope you enjoyed it, hope you learned something, and see ya!